Hello and welcome back to the last lecture of this NPTEL lecture series on thermal physics. Now, this week we have discussed about blackbody radiation, and we have seen that keeping in mind the similarity between blackbody radiation and an ideal gas assembly, if we decide to treat blackbody radiation as a thermodynamic system, we can get quantities like entropy. We can derive or we can describe an isothermal and adiabatic process in a cavity radiation. We can also compute all the free energy or energy functions, and not last but not the least, we can also derive or we can also discuss a phase transition in a cavity radiation. Now, one aspect of cavity radiation that I have omitted, and initially I thought it's not very important because we are not going into the details anyway, but then I thought, okay, so better to give a very short perspective on that, and that is the blackbody radiation of or the Planck's law of blackbody radiation. Now, what is Planck's law? If we look into it, if we look into the energy density as a function of wavelength or frequency, both ways it will look the same. The plot looks something like this. Now, these are not, strictly speaking, these are not the experimental plots. These are also theoretical simulation, but let me tell you the the matching between the matching between theory and the or experiment and the theory that was derived by Planck is pretty remarkable. So, initially, let us assume for now that this red one, for example, is a what you call the experimental data, which it is not. But so initial attempt was to and by the way, what is cavity radiation? I mean, where to measure this energy density? It is not along the body of the along the surface of the black body, because black body are typically made, the surface are made reflective, and what is a poor absorber is also a poor emitter. So, we have to concentrate on the radiation that comes out of this opening, tiny opening of the black body. Now, the early attempt in order to explain the shape of this black body radiation curve was given by Rayleigh and Jeans. So, they had a classical approach, that is to say, so that and they could explain the long wavelength behavior of black body radiation pretty well, but it failed miserably towards the short wavelength range, and this is what is called ultraviolet cataphore. Then came Wien's displacement law, which actually talks about the the location of the maxima as a function of temperature. So, according to this law, the product of the maximum temperature or the temperature of the cavity and the maximum of the this distribution function is a constant. So, if the temperature falls because it is a constant, so the maximum value should shift toward right. Okay. So, now these things, it was individual, it was discrete attempts to explain the blackbody radiation, but finally, when Planck came up with his rule or his laws of blackbody radiation. So, basically he came up with the concept of quantized photon energy. Only then he could actually compute actually work out a theory that can explain this curve with very good accuracy, and it turns out that in certain limits it can also give it can also give Rayleigh-Jeans law, and Wien's displacement law also comes out of Planck's theory. Now, this I have not discussed primarily because this type any discussion on quantum mechanics should start from this point. So, this is primarily the old quantum theory, and not much to do with the thermodynamics. Some statistical mechanics definitely, when what Planck used in order to explain, get to his results, but primarily some statistical mechanics and quantum theory. So, that is why I have omitted this from our earlier discussion. Anyway, so I thought it is better to have a quick look at it. Now, apart from this, the last topic which we are going to cover today is the topic of low temperature physics and third law of thermodynamics. Now, what is third law of thermodynamics? That we will come back to that. But before that, let me give you a very brief history of low temperature, or we can also call it the race to absolute zero. So, here in this, at the end of this arrow, we have T is equal to 0, which is the absolute zero temperature. So, all the temperatures are in Kelvin, by the way. So, this is the absolute zero temperature, and let us quickly look into the progression with time with in the modern history towards this absolute zero. Now, snow or ice or whatever you might call it, the temperature of that, the maximum temperature that we can have in a snowy day is somewhere around 0 degree centigrades, maybe slightly higher, maybe slightly lower, I mean could be lower than 0, but around 0 degree centigrades. But even in the cold country, for example, Central Europe, Russia, some parts of US, also in India, the Himalayas, the temperature can go much lower than that. Now, typically a cold day in central Russia, or in the peak of some tall Himalayan mountain, we can have the temperature might go down to -20 or sometimes even -30 degrees centigrades. So, let us say we have T is equal to 250 Kelvin. Now, that is naturally occurring. So, why I gave 250 Kelvin? So, this is probably the average low temperature that occurs naturally in Of course, we have a record low, I guess record low is somewhere around -45 degrees centigrades, but that is only a special case. So, we are not going into that. Now, 1823 Faraday uses, and historically speaking, people used to mix different salts with ice in order to produce ice cream and other cold food items. So, people knew that a mixing of salt with ice reduces the temperature further below the freezing point of ice or melting point of ice. Now, Faraday used a similar technique. He used he could reach all the way down to 208 Kelvin using a freezing mixture, so that he could liquefy ammonia. That is 1823. 1876, then it's only a very brief history. So, there has been lots of development in between times, and between 1823 and 1876, the laws of thermodynamics took its shape, especially the second law took its shape. People could understand the working principle of refrigerators, working principle of engines. So, when Linde came up with what Claude and Linde did was actually they machinized the procedure of liquefying gases. It's not only a freezing mixture anymore, but there are certain machinized compressor parts, and they could liquefy air at around -85 Kelvin. Now, liquid air temperature is kind of midway between liquid nitrogen and liquid oxygen temperature, these two values. So, it is approximately -85 Kelvin. It took another 20 years. To go down to liquid hydrogen temperature, that was developed by James Dewar in 1898, and another 10 years to liquid helium temperature by Onnes in 1908. So, liquid helium temperature is 4.2 Kelvin, and very soon it was discovered that if we pump on a liquid, now we have learned phase transition, and we have learned if we reduce the pressure on a liquid, then it will start boiling at a much lower temperature, right. So, that we have seen, we have done problems, and the opposite is also true. If we pressurize a liquid, it will boil at a higher temperature. So, immediately it was discovered that if people start pumping on liquid helium, the temperature can go down even to 1.2 Kelvin. That is also possible, right. Then but again, the barrier was approximately 1 Kelvin. People could not go below 1 Kelvin, and another 25 years till William Gicco and other scientists, they came up. First, initially the concept was given in 1927, then experimentally it was described in 1933, the process called adiabatic demagnetization. So, the concept is the following: we have a magnetic salt, paramagnetic salt, which is exposed to a very strong magnetic field, and suddenly, and it is already at low temperature, roughly approximately around 1 Kelvin or so, that is cooled by liquid helium, and suddenly the magnetic field is withdrawn. So, then what happens? It is equivalent to an adiabatic expansion of the system. So, the magnetic ordering, the magnetic dipoles were already pointing towards the magnetic field. Now, when the magnetic field is withdrawn, they will be fanning out, they will be randomly distributed in all directions in the cost of internal energy, and the process will, this adiabatic demagnetization will reduce the temperature further, and it was found out that it can go down to 0.2 Kelvin. Another 33 years till the helium-3 dilution refrigerator was first invented in 1966. I should not call it, it was first invented, but using that refrigerator around 1966, it was possible to achieve a low temperature as low as 300 millikelvin. Okay. So, that is pretty low, and but it did not stop there. Another 33 years, a nuclear demagnetization method was used on a rhodium metal, and it could be cooled all the way down to 100 picokelvin, which still is the world record of a lowest temperature of an object. Of course, afterwards, like that is already like 23 years. Okay. So, in last 23 years, there has been many experiments, many attempts to reach even closer to absolute zero. People could go, I mean, there are occasions where 1 or 2 atoms or maybe a small group of atoms could be taken to a temperature close to 10 picokelvin or so, but those are, we cannot really call it a, cooperative cooling, because that happened only on a very tiny cluster of, local cooling, I would say, tiny cluster of molecules. So, still now 100 picokelvin is the lowest achievable temperature on a finite size object, right. So, that means although we are very close, as scientists are very close to absolute zero, we are still very far. Like in the scale, you see, up to this point the scale was going down in tens of degrees. So, from here to here there is an order of magnitude, and after this 4.2 Kelvin mark, then immediately after that there is a 1 Kelvin is also around this time. After that it went down to 0.2 Kelvin in like 25 years. Next 33 years it went down by another 2 orders of magnitude, and next 33 years it has all went down by another 2 orders of sorry, not 2, it's more than milli to pico. So, it is, oh, it's huge. So, -3 to -12. So, 9 orders of magnitude, but this absolute zero is still far, yet we are very close. That, I mean, now we the intuition worked a long time, I mean long time before this temperature was even thought of, right. So, it was 1906 when scientist W.H. Nernt was measuring the specific gravity the specific heat of series of chemical salts. He came up with the observation, and he eventually came up with a theorem called the Nernt's heat theorem, that says for any isothermal process involving only phases in internal equilibrium, okay, the entropy change tends to 0 as the temperature approaches absolute zero. So, this is a so there are many different versions of this. This was definitely not the first version of this theorem or law, whatever you call it. So, initially he gave some statement, later on it was found out some improvements is needed, there are scopes of improvement, and eventually the present form present acceptable form is, for any isothermal process, the entropy change goes towards 0 as the temperature approaches absolute zero for the systems or only pure phases in an internal equilibrium. Right. Now, another few years down the line, Planck modified the statement slightly and said for any pure substance, the state at t equal to 0 is can be called a standard state. Standard state means it does not matter how we reach there, but once we reach there, it will be used as an universal reference, right. So, he said that t equal to 0 is a standard state and the entropy of that state is 0. Please note the condition that for any pure substance, and it is understandable that any pure substance, I mean it could be what I mean to say by pure substance is it is not an element, it's not necessarily an element, but even if it is a compound, the compound is in its purest possible form, no defects, no impurities, nothing. And it is understandable that this low temperature only one possible state of matter exists, that is the solid state. So, that means what he meant to say is, or what he said is, there are other alternative version of this statement that says for a pure crystalline solid, the state at t equal to 0 is a standard state where entropy is 0. Okay. So, I purposefully did not use the word crystalline here, because there could be other systems also which are we actually statistical mechanics also allows to observe or predict the entropy of other systems close to absolute 0, and the systems might not be solid which we can think of. It could be a spin system, it could be an amorphous glass. So, we will come to that, we will discuss that towards the end of this lecture. Anyway, so that was Planck's statement, and what does it mean? Mathematically, it means that limit t tends to 0, S is equal to 0 for any pure substance. Now, there is a subtle difference between what Nernt says and what Planck says. Nernt says that the delta S becomes 0 as t goes to 0. So, that means the change in entropy, and Planck says no, it is not the change in entropy we are talking about, it is the absolute entropy that goes to 0 as of a pure state goes to 0 as we approach absolute 0. Right. Now, this has even more furthermore, I mean it is a far reaching implication, because for any state, let us denote this by A. So, we can write the entropy, corresponding entropy at A as S bracket A. So, S of A, and we know that entropy calculation is typically done on any reversible path. So, that means the integration delta q r means reversible by t has to be evaluated along any reversible path, and we can always compute the difference between the initial and the final state. So, S A minus S of t equal to 0, which is essentially by Planck's Planck's theorem, this is equal to 0. So, that means this is equal to S A, this is equal to integration 0 to t delta q r divided by delta q r times t. So, this means this r stands here for reversible changes. Now, this rule is generally applicable with few exceptions, for example, in amorphous solids and in half integer spins, and sometimes this statement itself is mentioned as the statement of the third law. But it so happens that there is a much more general statement of third law, which from which we can eventually mathematically derive this particular statement, and that is the third law of that statement is actually called the third law of thermodynamics. Please remember the statement I am going to tell you. So, in some of the books you will find the Nernt's statement and Planck's statement is also mentioned as third law. Now, that is fine, because it can be proved, the equivalence of these laws can also be proved. Similar to the second law of thermodynamics, where we have a Kelvin-Planck statement and we have a what was it, Clausius statement and the equivalence of those can be proved. Now, what is the statement? The statement is, it is impossible by any procedure, no matter how idealized, to reduce any system to absolute 0 in a finite number of operations. Now, this is a very strong statement, and once again, like the first law and the second law, this statement cannot be proved. Okay. So, this statement has to be accepted so that we can prove the heat theorem, and also there are ways of somehow show that if the heat theorem, that means this particular statement is valid, then this also indicates to this particular statement, but I prefer to believe that this is a much more comprehensive form of the third law of thermodynamics, and heat theorem given by Nernt or Planck is only a corollary of this particular statement. Okay. Okay. So, this is the one, and once again we cannot prove it. We will not go into the details of how to show the equivalence, or rather how to prove Nernt's theorem from this particular statement. If you are interested, you can look into any standard textbook, and there are some discussion, certain discussion on this particular particular topic. But what we are going to do is, for the remaining of this lecture, we will be talking about the consequences of this third law. Now, what happens to the heat capacity? Delta S is equal to S of T2 minus S of T1. That means integration T1 to T2 Cx dt by T, where Cx is the heat capacity. Now, x could be P or V or basically anything. I mean, it is not necessarily that one process is either isobaric or isochoric. It could be any other arbitrary process. It can be performed along an allotrope or polytrope or any other path. But in general, we can, for any process, we can write a heat capacity Cx, right. So, x could be P or V or could be anything. But what is important here now, if we focus on the integration into the mathematical expression for integration and set T1 is equal to 0. So, that means S of T1 goes to 0 according to, so assuming that we have to, okay. So, here we have to accept the the what you call the equivalence between the third law of thermodynamics and and Planck's statement. So, that means according to, we can say according to third law of thermodynamics, S of T1 is equal to 0 as T1 tends to 0. So, that means delta S will be simply equal to S of T2, and for S of T2 becomes finite, this integration will be 0 to T2 some Cx dt divided by T. Okay. Now, in the lower limit what happens? If we integrate it and if we put the lower limit, then the integrand, or rather even before integration, if we just put the limits in the integrand, in the lower limit the integrand will diverge. So, this integration cannot be performed. So, from pure mathematical consideration, given that S of T2 has to be a finite quantity, we can say that as T1 goes to 0, Cx or the heat capacity also needs to go to 0 for any pure state. Okay. Because please remember, the Planck's statement is valid only for a pure state here, right. So, for any pure state, as the temperature goes down, both Cp and Cv, however they behave, okay, at higher temperatures, they must approach 0. And this is something that we have already seen. Remember the Debye theory of Debye T cubed law from specific heat of solids, right. So, we have seen that at very low temperature, the specific heat of a solid behaves as if it varies with T cubed, and as T goes to 0, T cube also goes to 0. So, we have already seen this is happening in practice, right. Now, for the expansion coefficient, the volume expansion coefficient, for example, this is alpha is equal to 1 over v del t p, and we use the thermodynamic relation that del S del P T is equal to minus del V del T P. We can write alpha is equal to minus 1 over V del S del P T. But as delta, when we go towards absolute 0, the isothermal expansion coefficient, isothermal volume expansion coefficient also goes to 0, because this is a change in entropy. So, delta S, as T goes to 0, delta S also goes to 0. So, we have alpha going to 0 for any pure phase. So, and interestingly, this is not only valid for pure phase, but for any object, because only for pure phase this is absolute necessity. But in general, if we accept the heat theorem by Nernt in its original form, then delta S going to 0, delta is equal to 0 as T tends to 0 for any substance. So, for any substance, not only for pure systems, we have alpha goes to 0 as T goes to 0. And without surprise, as for any object, Cp minus Cv is equal to T V alpha del P del T V, we can also write delta as alpha goes to 0 as T goes to 0, that Cp minus Cv goes to 0 as T goes to 0, which is also obvious from this. The difference between Cp and Cv diminishes as we approach towards low temperature, and at T equal to 0, the difference should also be equal to 0. So, that means at Cp and Cv both should follow, both should converge or confluence at one single point. Okay. And the value should be equal to 0. So, there is no heat capacity whatsoever at 0 temperature for any object. Right. Now, what happens to the free energy functions? There are two free energy functions H, F and G. We see F is equal to U minus Ts, and G is equal to U plus PV minus Ts. Now, for an isothermal isobaric change, if that means change occurring at constant temperature and constant pressure, delta, we can write delta F is equal to delta U minus T delta S, delta G is equal to delta H minus T delta S, where delta H is equal to delta U plus P delta V. Now, in the limit as T goes to 0, delta S also goes to 0. Once again, we do not have to have a pure system for this. For any system, T goes to 0, delta S goes to 0, and we have delta G is equal to delta H and delta F is equal to delta U. So, that means if we plot the two change in enthalpy and change in Gibbs free energy in the same plot, we should get a confluence. Once again it will confluence to a single point as temperature goes to 0. What happens to delta F? Delta F will be equal to delta U, and that should also go to 0, because as entropy approaches 0 at low temperature, so the internal energy for at least for a pure system also should go to 0. Now, what happens for impure system? Let us discuss that. Now, according to statistical mechanics, you remember in lecture 45 we have given this relation without proving, of course, because this is the proof of this lies in the domain of statistical mechanics, which is beyond the scope of this lecture series. S is equal to Kb ln W, where Kb is the Boltzmann constant, W is the number of microstates or configuration of the system in question. Now, if we put S is equal to 0, it gives W is equal to 1. So, that means at absolute 0, there is only one configuration of a pure state possible, and that makes very much sense, because if we talk about a pure system at absolute 0, what is that? A pure system is a perfect crystal without any defect, without any impurity in it. It could be a compound, it need not be a need not be an element, crystal of an element, but it has to be pure and defect free. So, in those case, if we even have 1 billion number of atoms or molecules present in that, they has to be arranged. There is only one way they can be arranged, so that there is a pure crystal present. So, there is only one unique configuration. Please remember that at t equal to 0 all the vibrations die, forget about rotation. So, there is no movement of the molecules, no movement of these atoms or molecules whatever, and they are sitting exactly at the place they are supposed to be. So, this is a perfect crystal with only one configuration possible, and that is why we get W is equal to 1. But then what happens for in not so pure systems? We can have systems, statistical mechanics, I mean from statistical mechanics it can be shown that there are systems where for example amorphous solids or half integer spin system, even at t equal to 0 they possess a good degree, high degree of degeneracy. They can possess high degree of degeneracy, so that W is greater than 1, that means S will not be equal to 0. So, for those type of systems even the delta U will not be equal to 0. So, delta F, you know, that relation delta F is equal to delta U at t equal to 0 is still valid, but for those non-pure systems delta U will not tend to 0 value as the temperature goes to absolute 0. Okay. So, there will be some unrelaxed this one unrelaxed Gibbs free energy, sorry Helmont free energy, or some internal energy, and also there will be some finite entropy for those type of systems. So, this is not a violation of the third law, I would say, but this is something that has to be learned, I mean that has to be understood only from the perspective of statistical mechanics. Okay. So, this actually concludes our discussion on thermal physics, and I do not want to summarize what we have learned in this last 12 weeks, because this summary will itself take a long time. But all I can hope that you have enjoyed the session as much as I did, enjoyed the discussion forum as much as I did, and you have, most importantly, you have learned something from the course. That is all I can hope. And finally, I would like to say thank you to all of you and to the entire NPTEL team for their wonderful effort and support, and also I want to thank you for your participation. Have a good time ahead and goodbye.